So Ken Hanley is a global director for 3M, 3M Advanced Manufacturing Materials Division. He leads the global research and development of new ceramics, way to go, fluorinated materials, there we are, glass additives, and ballistic armor and helmets in the 3M Industrial Materials Group. His 3M career has spanned 18 years, and he is credited with 13 inventions and 27 3M Gold Step Awards for successful new product introductions. Please help me welcome Ken Hanley.
Thank you. It's a tremendous honor to be here. Wow, what an audience. If I seem a little bit nervous, it's probably for two reasons. One, this is the first time since graduating that I've had to present in front of my advisor, Tim Lodge. Bringing back a lot of memories. Second is my daughter just texted me and said she got her driver's license today and she's taking my car tonight. So, we'll see. Real quickly, I'm going to go through a story of a challenge that I had. So when I moved into what we call Advanced Materials Division at 3M a couple of years ago, about 5 years ago, in reinventing a fluoropolymer business, a very mature business at 3M. And to give you a little bit of insight into some of the things that we do at 3M as well. So real quickly, Advanced Materials Division is a bit unique at 3M. So 3M makes quite a bit of finished products. We're actually the only division in the company that makes materials. And we sell those materials to other companies who do great things with them. And we probably have one of the most diverse portfolios in the company. And you can see it ranges from ceramics, ceramic fibers. You can see the fluorinated portfolio, glass bubble. There's things even on that we didn't put on here. It was mentioned we make all the ceramic body armor for the U.S. military. I wish we didn't need that, but we do. And some of that technology comes out of this division. So today what I want to talk about is our Dyneon fluorothermoplastic business, and we include Ptfe in there. And let me get through all this animation. 3M is great at a portfolio of acronyms, right, as you can see. But this portfolio, from tetrafluoroethylene to a modified version that we call PFA, fluorinated ethylene propylene, our partially fluorinated molecules, or ethylene tetrafluoroethylene, this really interesting material that we call THV, which is a terpolymer of TFE hexafluoropropylene and vanillin fluoride, and then we make PVDF homopolymer as well. And these things are used in essentially any application that really requires extreme resistance to temperature, chemical, outdoor UV stability. And you can run through wire and cable, polymer processing, molded parts, metal coatings. We've been selling into these industries for over 70 years. And so a little bit of the story I have to tell, though, is as 3 example applications, the business is pretty mature. We're looking for new growth opportunities, and I'll get to a couple here in just a second. But so, for example, you can see THV is used to limit the emissions through fuel hoses. And the rightmost two there on the graph are some THV materials, and you can see compared to silicones and HMBR, we're drastically able to reduce the emission with this great polymer. The problem is it's for a combustion engine, and that market is maturing quite a bit, and maybe even in some bit of decline. 2 other examples I'll give you. So US Bank Stadium, the panels up on the roof are actually made out of our ETFE. Those glass panels, if they were glass, extremely heavy, and so we worked with the engineers to build on something that's much more lightweight. It stays clear, and it's outdoor durable. Problem is, we don't get to build too many of those US Bank Stadiums very often. Great win, but maybe not a huge business. Lastly, Ptfe, great material. I'll come back to it at the end. It's used everywhere to line these pipes, reactors, so forth. The application hasn't really changed in a long time. It's still used, and there's a lot of competition in the space with polytetrafluoroethylene. So what did we do? So this is a representation of the 3M technology and how we look at it, of course modeled as a periodic table. But what this reminds us at the company is no division owns a single technology, right? The technologies are owned by the corporation, they're shared across divisions. And in a case like we had where we needed to reinvent this business, our fluoropolymer business, our division was quite capable. But if we worked with some other teams around energy components and particle dispersion processing, we could come up with some new stuff. And one of those that came up was a proton exchange membrane. So for those of you, this is a simple schematic of how a proton exchange membrane that goes into a fuel cell works. Hydrogen is split on one side. Protons go through the membrane. Combined with oxygen form water, you get power out of it, of course. So this is an electric vehicle application. And the cool thing that worked for us is that proton exchange membrane obviously has to have very high conductivity. But I'll tell you, the difficult part in that application is the strength, right? You get hydroxyl radicals, they chew up most polymers. It tends to be a very harsh environment. So this idea of a ionic fluoropolymer came up. We of course pursued it, but before we sunk too much investment in it, we want to understand the application a bit. And so I'm here to share that there is a market for fuel cells. I know electric vehicles are typically associated with battery, but if you think about heavy commercial vehicles, for example, an 18-wheel semi that's made for transporting weight, the battery itself would be a 5,000-pound battery. Its distance would be limited and its recharge is very long. Fuel cell has the advantage of much longer range, up to 1,000 miles, faster recharge times, and in a weight ratio, much lighter. So there is a need for garbage trucks, commercial vehicles, especially vehicles with defined routes, or high traffic devices. If anybody's been to Amsterdam and been in a Tesla taxi, if you ask that driver, how many Teslas do you own? They'll typically say 3. Because they have to have 3 going if they want to work all day. They run it to the end of their battery, they drop off and charge it and move into their second one and do that time and time again. That problem gets quite a bit easier with a fuel cell. There's always a question of, well, is it really coming? And so I would offer, yes it is. This is an example of the infrastructure, right? People claim, well, where am I going to refuel this? I was shocked to learn as we moved through the program, these are all representations of all the hydrogen refueling stations that you can find. You can travel pretty much across the western side of Europe in a hydrogen fuel cell vehicle if you wanted to. Japan's got close to 100, and of course on the west coast of the United States there's over 40. So these stations are being put in, the infrastructure is coming. And there's quite a bit of investment. So this is a quick list of some of the major players in this industry and how much they've already pledged to developing and commercializing fuel cell vehicles. This is separate from the battery powered. This is just on fuel cells. South Korea is putting in over $2 billion. Honda's got an $85 million production facility. It's a rather small number compared to the others, but the state of Bavaria gave us a couple $1 million to just move forward with our program with no commitments whatsoever. Just liked our research, wanted to support the development, so we benefited. The graph on the right is also interesting. This is a survey of the top automotive executives across these topics or trends over the past 5 years. And you can see fuel cell has risen from number 7 to number 1 on their concern list or investment list. So this is top of mind in the industry, and we think this market is coming. So here's our molecule in the upper right. So what we developed was a copolymer of TFE and a perfluorinated sulfuric acid, sulfonic acid. And on the bottom is a comparative competitive polymer. And the science that goes into this is this delicate balance. We think we have the world's best ionomer because you're trying to balance efficiency, which some other molecules may have slightly better conductivity or efficiency. But our molecule's got the durability that's needed in the application. It's got to be processed at high volume into a thin membrane. It's got to perform. And it's really this balance of properties that we think is really important. and we've now launched this product. It's in a few vehicles that I can't tell you about just yet, but it'll be out on the roads here pretty quick. And the sales have actually quadrupled each of the past 4 years. So it's a small base. We're starting from zero, but very encouraging about this business. So the next one to talk about is what happens. You take our fluoropolymers, combine it with some additive manufacturing and radiation processing. And this is really a story about Ptfe. Ptfe, for all practical purposes, is a fantastic material. You can see the wide-ranging requirements or performance, dielectric, huge temperature range, low surface energy. The problem is it's horrible to process, right? It does not melt, at least very easily. You're typically making very simple shapes with a lot of subtractive manufacturing. If you want to make anything complicated, you're going to have to wait to machine it. Molding is extremely difficult. So what we did is we invented a process to 3D print Ptfe. And so now essentially we can make any structure that you can put a design file into. These are representation. It was a tremendous project by the team. It involves printing a hydrogel with suspended Ptfe. And then we go through some complicated processing where we essentially slowly remove the water and the UV organic components, and what we're left is engineering grade Ptfe. We always get the question, well, is it really good Ptfe? And I would subscribe, yes it is. You can see the two density ranges. We're right in that range for having fully densified Ptfe particles. The mechanical properties are all very similar. A quick comparison of a cross-section of what a traditional Ptfe looks like in our parts, and we've pretty much got engineering grade Ptfe. And what this allows us to do is, remember back to the beginning, we're a material supplier. And so for us to continue to capture value, we wanted to move into the parts business. So as part of this project, we designed and launched a manufacturing business for making these parts, not just the material. So our business model here is if you have an application for a Ptfe part that can be made via additive manufacturing, we work with you, submit the designs, and we are in-house manufacturing this. Matter of fact, the facility is in Menominee, Wisconsin, one of our 3M plants. And we're open for business. And we've seen tremendous interest. These are just some of the parts. Static mixers, impellers. In some cases, just very small parts, even if they're simple, are a great fit with additive manufacturing because they're difficult to handle with typical subtractive techniques. And we're open for business. And with that, I will take any questions.
We have time for questions.
Right. Sir.
What have been some of your processing challenges moving from the whole fluorocarbon business to what you're doing now?
Yeah, so emulsion polymerization, and obviously you've heard some, the production of high molecular weight fluoropolymers with making minimal low molecular weight or residual fluorinated materials has been our emphasis for the past 15 years. We moved out of what was called the C8 chemistry, moved down into C4 chemistry, and a lot of the molecules here I'm showing today have zero residual small molecule fluorinated species. That's tremendously difficult, and that's been a big part of the program.
What's your minimum line resolution that you can resolve with your printing process in that polymer?
Well, that's a good question. I believe it's around 10 microns, but I will look that up for you. One of the things that we got was actually just a smoothness that we can get in our process compared to the roughness of machine parts because they only have so much resolution in that subtractive process. Thank you for your time.